All right. Good morning again, Michael Prince, and now we are joined by Syra. Okay. Parang ang bilis ng panahon, no? No look now, and on Friday, first week na ng April, and I know many of us are excited para sa April kasi the first 2 weeks would be medyo bakasyon for us, right? We're gonna have the reading break April 2 to 8. And then right after that, meron tayong Holy Week, time to reflect and probably relax a little bit more. All right. Pero before going there, siguro sana matapos natin yung module number 2 or yung unit number 2 for math 155. Okay. Oh, by the way, I have graded, I think, all of the problem set submissions. So kindly double check, pabasa ng comments, and then pa-double check ng score sa Canvas. If you submitted the problem set, say via email, and I haven't returned it to you yet, please let me know kasi natabunan na siya malamang. Kasi what I know or what I assume is I have graded everything already. Okay? What else? Let's see. Mukhang yun lang naman. How was the problem set? Natanong ko na ba kayo last week? Parang natanong ko na pala kayo, no? So, yeah. Problem sets will be like that unless you have some qualms or you have some reclamos. So just let me know what you think about it, okay? Send me an email or send me a chat if you don't want to share it in public, all right? Okay, so some random thoughts. Simulan natin siguro yung klaseng ganito kasi sa kumustahan, di naman kayo nag-aambag eh. Hindi naman kayo nagko-contribute. Tayo nyo mag-share. So ako na lang, mga random thoughts, right? So siguro over the weekend, of course, we are still bombarded with election-related news. Ano? Some of the things or some of the articles I read reminded me of this thing, which initially I found out I read about first in a Facebook post. It's like a meme or a random post by somebody years back. Okay. And it's about this story about the US Army trying to see how they can improve yung kanilang mga planes during the Second World War. So, of course, in a war, usually kapag meron kang superpowers that are at war with each other and they are almost at the same level of technological advances, right? Usually the winner is based on how many of their Class A weapons survive, like airplanes or military jets and so on. And kung sino yung nakakapag-sustain ng mga rations nila sa kanilang mga troops on the ground. And so that's why in the Second World War, there was a big explosion of researches on how to improve processes, right? So isa sa mga offshoots or products of Second World War ay yung modern day operations research, right? How to efficiently design your processes para makuha mo or ma-obtain mo yung desired effect, right? Now, dun sa isang experiment ng US military. So, gusto nilang i-reinforce yung mga planes nila. All right? So, tingnan nila, ano dapat yung kailangan nating ilagyan ng further armor para makasurvive yung mas marami nating plane, right? Because they cannot just put armor over and over again on all layers of the aircraft kasi masyado siyang bibigat. So, magkakadrag and then other factors will kick in. Hindi na magiging efficient yung paglipad niya. So, gusto nilang i-reinforce yung mga certain parts. And what they did is to analyze yung mga planes na bumabalik. Tinignan nila, etong mga planes natin, saan ba yung mga bullet holes na nasustain nila? All right? And a typical scenario is like this one in the picture here, right? So makita niyo sa wings, dito sa middle ng body, saka dun sa tail, maraming mga bullet holes. And they initially concluded that, okay, para increase yung survivorship ng ating mga aircrafts, why not put extra armor dito sa mga parts na to para hindi siya magkaroon ng para hindi siya mag-sustain ng heavy fire, right? Now, there's mathematician who said that was erroneous or that reasoning was erroneous, and it was Abraham Wild. Okay. Sabi niya, hold on, medyo may flaw yung reasoning niya na yan. And can anybody among you guess what's the wrong thing about that? Ano yung napansin ng mathematician na to na, oy, mga generals, mali yung strategy niyo? Do you think something is wrong with that approach? Kasi sa unang tingin, mukhang, oo nga, no? Medyo tapalan natin yan ng heavy armor para walang bullet holes, right? Sige, Zaira.
Ask ko lang po kung naka-share screen po pala kayo kasi po wala po akong nakikita.
Yeah. I'm sharing my screen pero hold on, restart ko para...
Sagutin ko na lang din po yung tanong po.
Ayan, pilitan tuloy si Zaira. Go, Zaira.
Parang nabasa ko na rin po siya. Parang ang ginudge po nila ay yung mga planes po na nakabalik. Pero hindi po nila nakita yung mga planes na naiwanan po sa war po, sa battlefields po.
Mm-hmm. Yeah, great. Thank you, Zaira. That's exactly the point that Wald was making, right? So, yeah, tama siya. Kasi ang ginawa nila ay inanalyze nila yung mga nakabalik. All right? And the implication of that is nagkaroon siya ng tama dito sa mga highlighted parts and yet this aircraft survived. Ang sabi ni Wald, ang kailangan nating i-reinforce ay itong mga parts na walang tama. Kasi malamang yung mga plane na hindi nakabalik, yung mga hindi nakasurvive, sustained hits near the engines and near at the spark, kaya hindi sila nakabalik. All right? So this is called the survivorship bias. Survivorship bias. Okay. Or the immortal time bias, which is an erroneous logical, which is a fallacy that means na ang pinag-aaralan lang natin ay yung mga nakasurvive sa isang event. And we are usually deducing some information or deducing some arguments or some insights from only looking at the experiences of those who made past a certain historical event. So, ibig sabihin, mali, natingnan mo lamang ano yung meron dun sa mga nakasurvive. And we are often disregarding those who didn't survive or those who are not present to share their stories about a certain event, all right? And that made sense. And it was already proven in the Second World War that doing this, okay, or avoiding survivorship bias is effective in attaining your goals. So I hope we learn from history. So hindi lamang kailangan ang tinitingnan natin ay sino yung mga naging successful o sino yung mga nakasurvive during a certain event, right? We must also look at those who are not present to share their side of the story. Okay? So yun lang, yun yung random thought for today. So I hope nakikita na yung screen ko. So, yeah. Okay, back to regular programming. All right. Oh, by the way, I hope yung mga reminder deadline nung reaction paper for the IMSP research webinar on Friday, April 1st, right before midnight. Bawal na kasi magpa-submit starting April 2 because of the what do you call this? The reading break. So pasa nyo na siya. It's just a short reaction paper. So sayang yung bonus dun sa problem set, especially if may hinahabol kayong score mula dun sa mga problem sets. Okay? Okay, back to regular programming na talaga. So last time we were talking about, or actually we started talking about sequences, and actually last meeting we talked about order limit theorems. And basically, ito yung mga theorems that tells us that the natural ordering, ibig sabihin yung less than or greater than relation, is preserved in taking limits. So that means if you have two sequences kung saan sila ay parehas convergent, tapos the terms in one of the sequences is always are always larger than their counterparts in the first sequence, then the limit of the second sequence is greater than the limit of the first sequence. All right. And ano pa nga ba? We also seen the squeeze theorem. Okay. Which is a very powerful tool, not only computational wise, but also improving some of the results, as we will see later. Maano natin siya, makuquote natin siya in improving some of our main results. And then, ano pa nga ba? We talk about subsequences as well. Which is basically you have a sequence and then you pick some terms from this sequence to form another sequence in such a manner that the ordering of the terms are preserved. Meaning kung sino yung nauuna dun sa parent sequence, siya pa rin yung mauuna dun sa subsequence, right? And we have said that meron tayong equivalent statements last time na kapag ka meron kang isang sequence, tapos siya ay nag-converge, right? Then we are sure that, or actually, this is equivalent to saying that any subsequence will converge to the same limit A. All right? So, pero meron kang convergent sequence kahit anong convergent subsequence, or actually hindi ka sure tayo na kahit anong subsequence ay lagi magko-converge. Kung nag-start ka sa isang parent sequence na convergent kay A, kahit anong subsequence na buuin mo sa kanya, magiging convergent pa rin. And this is also equivalent to saying that yung even subsequence at saka yung odd subsequence ay magko-converge din kay A. Right? Which makes sense kasi sabi natin ang limit ay yung behavior dun sa dulong parte na ng listahan, right? So this is what happens at the tail end of our sequence. So kapag ka meron kang subsequence, hindi natin binabago yung order. So yung mga nasa dulo ng subsequence, sila rin malamang yung mga nasa dulo ng parent sequence, all right? Kasi the process will go on forever. So if the elements in the parent sequence approach a certain number, so mapo-force yung mga elements ng subsequence na mag-converge din dun sa kaparehas na limit or sa kaparehas na number A. Tapos special case lamang nung statement B, yung statement C. Kasi itong dalawang sequences na to ay by definition ay mga subsequences. So dapat mag-converge din sila kay A. Now that's quite natural. So you might think, wala naman to masyadong naidagdag sa ating knowledge because this makes sense, right? But I think one of the highlights of these equivalent statements is a divergence criterion. Kasi ang sinasabi natin dito, pag siya ay convergent, then dapat lahat ng subsequence niya ay magko-converge sa kaparehas na sequence, sa kaparehas na limit, all right? Now, a little analysis of that statement will bring us to a divergence criterion. Ano nga ba yung divergence criterion na na-establish natin last time? Kasi medyo mahirap na mag-prove ng divergence because we need to show that the sequence will not converge for any real number, okay? So, kaya mas minapadali nito yung buhay natin. It is telling us na kapag ka nakakita tayo ng dalawang convergent na subsequences, tapos magkaiba yung limit nila, then the original sequence will diverge. So basically, it's just up to us to creatively choose two subsequences coming from a parent sequence that will converge to two different numbers. Okay? Kasi papasok na yung contrapositive nung isa dun sa mga equivalents dun sa statement natin kanina. Alright? Kasi kung magko-converge siya, ibig sabihin dapat yung mga subsequences, lahat ng subsequence nagko-converge to the same limit. So pag meron kang dalawang subsequences na magkaiba yung limit, automatic magda-diverge na yung original sequence. And a great example or a simple example actually is the alternating sequence of ones and negative ones that we have seen before. If you remember, yung proof natin dito, hinati natin sa tatlo. Pinakita natin na kahit anong, na si 1, si negative 1, o kahit anong iba pang real number ay hindi pwedeng maging sequence, hindi pwedeng maging limit ng sequence na to. So doon natin napakita yung divergence niya. Pero with the aid of the divergence criterion, we can just say, okay, kunin natin yung even subsequence. Tapos kunin din natin yung odd subsequence. These two subsequences will just be consisting of constant terms, 1 and -1 respectively. And since they are constant sequences, then they will have limits. Essentially, yung limit nung even ay 1, and limit nung odd subsequence ay -1. We found two different subsequences that are convergent and converge to different limits. So by the divergence criterion, yung parent sequence ay hindi na hindi na magko-converge. All right? So this is one nice way in order to prove that the sequence is divergent. Actually, it also kind of makes sense kasi di ba dulo ng listahan. So ibig sabihin, meron kang subsequence na ang behavior niya dun sa padulo ng listahan ay palapit ng palapit kay -1. Samantalang meron pa tayong isang subsequence na dun sa padulo ng listahan ay papunta sila kay 1. So ibig sabihin, yung parent sequence will have some of its terms in the end or towards the end of the list. Pero wala nga tayong end eh. But I hope clear yung context pag sinabi kong tail end o yung nasa dulo ng listahan. Habang lumalayo ka sa listahan, may mga terms na pa-approach kay -1. Merong mga terms na papasok or papalapit kay +1. So basically, malilito ka ngayon. Kanino siya magko-converge talaga? Kay 1 o -1? Because there would be infinitely many terms that will approach -1, and there will be infinitely many terms that will approach +1. Okay? So I think dyan tayo natapos last time sa divergence criterion. So for today, we'll just do a quick discussion about infinite limits, and then we will jump into some of the named theorems, the big names in sequences, and actually some of them are also can be tackled in the context of functions of real variables or saan pa nga ba? Kahit sa topological point of view. But these are nice consequences or big consequences of the completeness axioms. And actually, I think all of them are equivalent to the axiom of completeness. So we could have rebranded our advanced calculus class by choosing one of these as our completeness axiom. Kaya lang medyo mahirap na sila yung gamiting completeness axiom kasi kailangan nating establish as our undefined terms, hindi lamang yung set of real numbers pero pati yung mga sequences. All right? Right. So first, tingnan muna natin yung konsepto ng infinite limits. Now, we say that a sequence diverge to positive infinity if and only if for each real number capital M, there exists an index capital N such that right after N, okay, so lahat ng mga little n's na mas malaki kay capital N, yung little n term dun sa term ay mas malaki na dun sa real number na yon. So what does this say? Pumili ka ng kahit anong real number, M, kahit gaano pa siya kalaki. Sure tayo na starting from an index, okay, there is a starting index after which lahat na ng terms dun sa sequence ay mas malaki kay capital M. And you can do this for any real number capital M however large it is. So ibig sabihin, pag binigyan kita ng 10 billion, kung nagda-diverge talaga yung sequence kay A sub M, then there will exist a starting point in the list such that after that starting point, all terms in my sequence will be greater than 1 billion. All right? So, and then you can do this for every real number. So essentially, pwede nating sabihin that the terms in the sequence will eventually grow without bound. Pataas sila ng pataas kasi nga, kahit gaano pa kalaki yung real number na i-imagine ko, laging merong simula na after that simula, mas malaki na lagi yung terms ng sequence kesa dun sa napakalaking real number na pinili ko. Alright? Now, analogously, we can say that the sequence diverged to negative infinity, even only if for each real number big M, there's still a starting point capital N, such that right after that point, a sub n will be less than negative m. Okay? Ito naman ay paliit naman ng paliit yung mga terms ng sequence, all right? Because you can think of a very large real number. Kunin mo yung negative niya, all right? So ito ay papunta ka na sa kaliwa ng real number line, pero meron kang isang number which is negative m na nasa super kaliwa na ng real number line, and yet you can find infinitely many terms of the sequence that are to the left of that negative number, negative m. Okay? Dapat pala ito ay I think this should be r plus, okay? Kasi dapat negative siya. And then this should be r plus. Okay. Ibig sabihin positive real number saka negative real number. Sorry, parehas positive real number yung capital M's dito. So kindly make those corrections. I think dapat siya ay positive. Okay, so let's see. Let's see this in action. So let's have example 2.5, and it is telling us what? Okay. We want to show that the limit of n as n approaches infinity is equal to positive infinity, which is basically, nakita na natin to, this is just the unboundedness of n, or the set of natural numbers in disguise. Kasi kung i-write down natin yung terms ng sequence na to, ang sequence na yan ay little n lamang, so this would be 1, 2, 3, 4, 5, 6, and so on, which is the set of natural numbers in its natural order, the increasing order. Okay, and we have known that the set of natural numbers is unbounded above. So ibig sabihin, itong sequence na to ay hindi siya dapat magko-converge. Actually, hindi lang siya hindi magko-converge, siya ay magda-diverge to positive infinity. Okay? Kasi meron dalawang klase ng divergence. Unang divergence ay hindi siya nag-approach ng isang certain real number. Yan yung pinaka-generic na divergence. Pero merong etong infinite limit, special type siya ng divergence, that we are sure that they will grow indefinitely large or indefinitely small, okay? Kasi magda-diverge siya to either positive or negative infinity. Hindi siya katulad nung negative 1 to the power n na divergent. Ibang klaseng divergence to. Kasi ito, hindi lalaki yung mga terms ng sequence, pero wala siyang patutunguhang isang direksyon. Alright? Pero pag divergent to an infinity, isang direction lang yung pinupuntahan ng mga terms ng sequence, pero indefinitely either to the left or to the right of the real number line. Okay? Now, hold on, guys. Excuse me. Okay, so now we want to show that indeed the sequence n converge or diverges to positive infinity. So what we want to do here is to show that for any positive real number we can think of, there is a starting index, capital N, such that ang a sub n ay mas malaki kay capital M. All right? But a sub n is equal to little n. So we want to show that there is a starting index capital N such that kapag si little n ay mas malaki na kay capital N, ibig sabihin si n dapat mas malaki na kay capital M kasi nagkataon na ito si a sub n. All right? And the proof really is via the Archimedean property. Tapos ito rin yata yung ginamit natin para ma-prove yung unboundedness ni n dati, right? So because this is essentially the same thing but in a different context. Now, by the Archimedean property, we are sure that there exists a real number capital N. Actually, hindi siya dapat hindi dapat siya element ni R. Tama ba? Yeah, I think this should be N. Bakit ang daming typo? Malamang hindi ko siya napansin last semester or lumang version yung ginagamit ko. But kindly correct that. Capital N should be a natural number such that capital N is greater than capital M. So pwede mong isipin ito, paano natin ito i-contextualize sa Archimedean Yan property. Ang Archimedean property natin ay for all epsilon greater than 0, there exists a natural number n such that 1 over n is less than epsilon. Okay. Or in other words, this is 1 over epsilon is less than little n. So ibig sabihin, ito yung natural number, tapos si 1 over epsilon siya si capital M. Remember, capital M, we want it usually to be a very large number, all right? Tapos yung epsilon sa Archimedean property, gusto ko siya ay napakaliit na number. So basically, an equivalent statement of the Archimedean property is we can always find the natural number that is larger than 1 over epsilon, okay? So yung 1 over epsilon, siya yung i-take natin as capital M because anyway, this will work for any positive real number. So kaya dapat positive real number si capital M. Tapos si little n ay natural number. So si little n ng Archimedean property ay gagawin ko capital N nitong problem natin. Alright? So basically, or pwede mo siyang isipin, unboundedness na lang ng ng set n. Kasi unbounded yung set n, kahit anong real number, meron kang makikitang element ni n na mas malaki kesa dun sa real number m na yon. Okay? And so that means that since this is true and little n is larger than capital N, so we're sure that little n is greater than capital M, which is basically the definition of divergence to positive infinity. Okay? So laging may starting index kung saan after that starting index, mas malaki na yung terms ng sequence n kaysa dun sa real number na napili mo kanina. Okay? So yeah, but that's not a new thing to us kasi napakita na natin yan before. Okay. Now, a natural question is, ano yung epekto nung bago nating definition in the context of the theorems that we have developed before. All right? Meron na ditong remark na yung squeeze theorem ay pwedeng ma-extend sa infinite limits. In what sense? If you have two sequences that sandwich another sequence, halimbawa, meron kang AN at saka si BN, tapos napapagitnaan nila yung sequence CN, all right? Tapos yung AN at saka BN both diverge to the same kind of infinity, meaning either both AN and BN converge to or diverge to positive infinity or they both diverge to negative infinity, all right? Then, dahil in the context of infinities, equal pa rin yung limit ng kaliwa at kanan, yung nasa gitna, si C sub n, ay ma-force to diverge to the same infinity to which nagda-diverge yung dalawang nagsasandwich sa kanya. Okay? So even though infinities are not real numbers, the results of the squeeze theorem applies or still apply to that scenario. Okay? Tapos ganun din yung order limit theorems. Yung order limit theorems natin ay pwede ring ma-adapt to accommodate itong divergence to infinity. All right? So basically, statements 1 to 4 in theorem 2.7 are the respective versions ng mga order limit theorems natin. Pero ngayon, may slight modification tayo to allow yung divergence sa positive infinity. So for instance, we'll tackle the proof of 1, okay? Na kapag ka dito pa lang assumption lang natin si A yan nagda-diverge kay positive infinity. All right? So if mali pala, hindi ordered limit theorems ito. Ito ay sa algebraic theorems, all right? So if AN diverge to positive infinity and the second sequence, the sequence BN is bounded below, ibig sabihin, pag kinuha natin yung sequence ng mga sum, right, sila ay magda-diverge pa rin sa positive infinity provided that Bn is bounded below. Right? So ibig sabihin si Bn hindi siya lumalampas, hindi siya mas maliit sa certain real number. So pag nag-add ka sa kanya ng mga ANs na in the long run ay palaki ng palaki without bound, so ibig sabihin itong sum hindi rin siya lalaki ng sobra-sobra. Lalaki pa rin siya ng sobra-sobra towards the end kasi ang driving force dito ay yung sequence sa yan. Okay? before we go to the proof, does the additional assumption that Bn is bounded below make sense? Can anybody give us an idea bakit kailangan na bounded below yung Bn? Bakit kailangan yung additional assumption na yun? Sige nga, tingnan ko. Kung kaya nyo imagine. Bakit ko kailangan yun? Yes, David.
Sir, kasi po baka hindi siya bounded below, di baka papunta naman siyang negative infinity.
Right, perfect. Thank you, David. Yeah, yun yung magiging problema. Kapag kasi Bn nag-diverge to negative infinity, mamroblema na tayo. Hindi na natin alam yung magiging behavior nung sum a sub n plus b sub n. So kung ito ay papunta kay positive infinity, so we can think of the an's to be very, very large positive numbers, and then bn to be very, very small negative numbers. So hindi natin alam kung ano yung nangyayari sa sum. Okay? Because we don't know how fast an and bn goes to their respective infinities, right? Kasi pagka mas mabilis nagpa-positive infinity yung mga an's, so sila yung magbubuhat doon sa behavior ng sequence. So posible siyang mag-diverge to positive infinity. While if bn diverges to infinity significantly faster than an, so dapat yung sum magko-converge siya sa negative infinity kasi ma-overshadow nung pagpunta ni bn kay negative infinity yung pagpunta ni an kay positive infinity. All right? But if they diverge to their respective infinities at roughly the same scale or at the same rate, so parang rate of convergence ito ano. So kapag halos magkasabay lang sila by some constant factor, then hindi natin alam kung saan siya pupunta. Posibleng pumunta siya sa isang constant. Alright? So yun yung problema natin kapag hindi natin in-assume na bounded below. This additional assumption guards us from the occurrence of an indeterminate case. All right? Yung kung maalala niyo yun sa Turkey series natin. Okay. Now, let's try to write a proof. Though nasa handout na yung proof, binura ko muna siya. Analyze natin siya. So, nung proof ni 1, so ang alam natin ay si Bn ay bounded below. Okay? So basically, I can just write that as Bn bounded below. So this is larger than or equal to, say, some m sub 0, which is a real number for all n in n. Okay? So bounded below siya, tawagin nating m sub 0. Okay. Tapos we know that a sub n diverges to positive infinity. Okay? So ibig sabihin naman ito ay for every real number m1, for every real number m, positive real number m, that is, there exists a starting index, capital N, in n, such that whenever little n is greater than or equal to capital N, then ang a sub n ay mas malaki kaysa kay capital M. Okay? Now, gusto nating ipakita na yung an plus bn ay magda-diverge din kay positive infinity. All right? So I want to show that for any choice of a real number, okay, I can always find a starting index such that yung an plus bn ay mas malaki na doon sa arbitrary positive real number that I have chosen, right? So I want to show that this is larger than any choice of positive real number, right? So after some starting index. Pero sino ba yung may starting index na dito? Si An may starting index na. Kasi alam natin yan ay mas nag-diverge to positive infinity. So maybe I can use the capital M here. Tawagin ko siyang M1 para ma-distinguish siya dun sa capital M na gusto ko dun sa sum. So I know that in the long run, yung mga ANs ay nagiging mas malaki kesa kay M1. All right? After some starting index, the ANs are larger than M1. And on the other hand, I know that the BNs are bounded below. Ibig sabihin, yung mga BNs, mas malaki sila kaysa kay M sub 0 for any for any little n naman. So ito, laging totoo. Alright? Laging mas malaki si Bn. Ito ay greater than relation, right? So laging mas malaki si Bn kaysa kay Mo. Si An, after some starting index, nagiging mas malaki kay M1. So ibig sabihin, after the same starting index as the starting index for An, yung An plus Bn ay mas malaki na kay M1 at saka kay M sub 0. But what is M1 plus M sub 0? M sub 0 might be fixed because it is a lower bound for the sequence Bn. But M1, oops, sorry. But what happened? Yeah. But M1 was chosen arbitrarily kasi si M1 yung nangyari, siya yung nagmula dun sa challenge kay An. Okay? So, ibig sabihin si M1 plus M sub 0 can be thought of as an arbitrary real number because of M1. Yung choice ni M1 ay arbitrary choice of a real number, dagdagan mo ng isang constant M sub 0 which is fixed, the result is still arbitrary. Okay? Kaya ito yung preliminary analysis. Bakit ang M napipiliin ko doon sa definition ng divergence to positive infinity ay si M1 plus M sub 0. Okay? Now, let's just write the formal proof. Okay? So, tago natin yung preliminary analysis. Oops. Okay? Now, kasi hindi naman required na isama yung preliminary analysis. So, okay. Maybe we can start by writing all of the immediate consequences of our assumption. So let's say since Bn is bounded below, then there exists an M0, a real number M0, such that A sub n is greater than or equal to M sub 0 for all natural number little n. Okay. And then moreover, we know that An approaches positive infinity. Then for any real number, inisip ko kung ano yung ibibigay kong capital M. Let's see, capital M. Tama ba na M1 yung gamitin ko? Okay, for any real number M, and then maybe for any real number M of the form M sub 0 plus M sub 1, okay, there exists a starting index capital N in N, kasi ginagamit ko ngayon yung definition ng A sub N, okay? Okay. Tanggalin ko muna to. Kasi tinatry kong dayain yung proof eh. Gusto kong capital M yung mangyari dun sa AN plus BN. Siya yung mag-appear dun sa AN plus BN. Ngayon, ang ginagawa ko, nag-apply ako ng definition ng divergence dito muna. So, kailangan piliin ko sino yung real number na gagamitin ko dun sa definition ng divergence to positive infinity ni AN para dun sa dulo ng proof, para dun sa AN plus BN, mapalabas ko si capital M. Alright? So, here may be, okay, for any real number M, okay, there exists a starting index capital N such that for all little n greater than or equal to capital N, we have the following inequality. A sub n is greater than M minus M sub 0. Okay? So ito ay si Ito yung medyo tricky. Kailangan natin dayain yung proof. M minus M sub 0. Okay. Now, M is arbitrary. So yung M minus M sub 0 ay magiging arbitrary rin. Okay? So ibig sabihin, pwede ito yung kunin kong capital M dun sa definition ng divergence to positive infinity, right? Because this is still arbitrary. I have an arbitrary minus a fixed number. So dahil ito ay arbitrary, real number pa rin naman si M minus M sub 0, then, okay, there is a starting index for which we are sure that A sub n is still larger than M minus M sub 0. Okay? Now, bakit ito nga ba yung gusto ko? Well, totoo to sa lahat ng little n na mas malaki kay capital M. So, okay, we'll have A sub n plus B sub n would be larger than, papalitan ko lang yung mga quantities na to ng mga mas malalaki sa kanila. And if I do that, I know that the new sum will be larger, will be smaller pala with this sum. So si AN at si BN, papalitan ko ng mas maliliit na numbers. Mali yung una kong sabi. Papalitan ko silang dalawa ng mas maliliit na numbers. So I am sure that this sum will be larger than the new sum that I'll be forming. Okay? So, pero saan nga ba si AN plus BN? Si AN, mas malaki siya kay M minus M sub 0. Tapos si BN, mas malaki siya kesa kay M sub 0 by our assumption. Sorry, kulang pa yata ako sa kape. So, dapat BN yung sinulat ko kanina. So, if I do those kind of mistakes, kindly call out me, guys, as early as possible, right? Para hindi ko siya ma-carry over dun sa proof sa baba. So, alam ko si BN mas malaki kay M sub 0. So, I can put it here, M sub 0. Right? But this guy is equal to capital M. Ito yung gusto kong pandaraya kanina dun sa proof, right? And now, let's review what we have found. So, we have found that for any real number capital M, there exists a starting index capital N such that right after that starting index, the sequence, the term AN plus BN is larger than capital M. So basically, this proves that AN plus BN diverge to positive infinity. End of proof. So you see, medyo pinaglaruan ko lang talaga yung definition ng divergence to positive infinity. Okay? Now, in the text, meron pang isang pinrove. I think it's 2 yata yung pinrove dun sa lecture notes. Tinakluban ko lang siya rito. Ayan, pinrove yung property 2, right? So, just kindly read it and then try to write a proof for part 3 and part 4. So that should not be, I think, too hard. Okay, kaya-kaya niyo yan, guys. And then I think there's a bunch of exercises here. Okay. Na-miss niyo na ba mag-homework? Pwede na ba tayo mag-homework next week? Hindi pala pwede, no? Kasi reading break. Certain nyo naman. So susunod na ay kailan susunod nating homework? Or ayaw nyo na mag-homework ever? Kasi nakaipon na kayong matataas na points. Ano? So siguro after, gusto nyo ba mag-homework sa April 11? Or mag-submit? Sorry, nawala ako for a second there. Alright. Okay lang ba after na lang ng Holy Week? Para wala tayong iisipin ng during the Holy Week, ano? So, kasi pag nagpapasa ako sa inyo ng April 11, kailangan ko mag-check ng Holy Week. Sabagay, penitensya, ano? Ay, pero hindi pala pwede kasi ibig sabihin na magtatrabahuhin ko kayo ng reading break. Bawal kayong magtrabaho ng reading break. So, okay, after na lang ng Holy Week. So, okay. So now let's take a look at some of the big names. Okay. So una yung Monotone Convergence Theorem. But basically before that, we need to talk about monotone sequences. But let me introduce the motivation behind the Monotone Convergence Theorem. Okay. Kasi we observed last time na kapag ang isang sequence ay bounded, kapag ang isang sequence ay convergent, magpa-follow na siya ay bounded. Alright? Convergence implies boundedness. So that's one of the results that we have earlier. However, the converse is not true. Alright? Kasi sa math, pag sinabi nating true ang statement, dapat true siya for all. Pagka may nakita kang isang case na siya ay false, kahit 100 cases na siya ay naging true, false pa rin yung statement. Because yung truthfulness sa math dapat universal. Hindi pwedeng may sarili tayong truths na pinapanghawakan. So, hindi pwedeng kanya-kanyang facts dito. So, true siya kapag totoo siya sa lahat. We are sure na kapag meron kang convergent sequence, kahit anong itsura ng convergent sequence na yon, siya ay bounded dapat. But the converse is not true. Kasi merong mga sequences, even though may mga sequences na bounded tapos convergent, meron din naman mga sequences na bounded pero divergent. For instance, yung paborito nating -1 to the power n. Siya ay bounded pero hindi siya convergent. Right? Pero yung constant sequences like a sequence of all ones, sila ay bounded, tapos sila ay convergent pa rin. So, ang tanong ay, meron ba tayong property na pwedeng idagdag sa pagiging bounded para mag-guarantee ang convergence? Alright? Kasi usually ganun sa math Gusto mo ng convergence theorems. Okay, na-prove ko na kapag siya ay convergent, dapat siya ay bounded. Next question is the converse true? If the converse is false, then pwede mo pang tingnan, next step sa research ay, ano kaya yung pwede kong idagdag para maging totoo yung converse? Alright? So in our context, ano yung pwede nating idagdag sa boundedness para mag-guarantee yung convergence? And it so happens that monotonicity is a sufficient condition that can be added to boundedness to guarantee convergence ng isang sequence. But what is monotonicity? Alright, kailan natin sinasabi na monotonic ang isang sequence o sinasabi na monotone yung isang sequence? Alright? Now, a sequence AN, so daanan muna natin yung pagiging increasing at pagiging decreasing, but you already know this, right? So the sequence AN is increasing kapag kang A sub n ay less than or equal sa A sub n plus 1. Habang lumalaki yung subscript, yung terms ay lumalaki rin. Alright, so yun yung pagiging increasing. Strictly increasing kapag strictly lumalaki. So nawala yung less than, yung equality doon sa dito sa statement o dun sa relation between two terms in the sequence, all right? And then, ganun din kapag decreasing. So may analogous definition. So a sequence is decreasing if A sub n is larger than or equal to A sub n plus 1. Tapos strictly decreasing siya kapag tinanggal mo lang yung equality mula dun sa pagiging decreasing. All right? Now, if your sequence always increases or always decreases, then we say that that sequence is monotonic. All right? So yung monotonic adjective siya na nagde-describe sa isang sequence. So ang isang monotonic sequence o ang isang monotone sequence ay either increasing or decreasing. Medyo strict yung monotonicity. Kapag meron kang dalawang terms na hindi sumunod dun sa pattern ng pagiging increasing or decreasing, hindi na siya monotonic. Dapat ang usapan is AN is less than or equal to A sub n plus 1 for all n, or A sub n is greater than or equal to A sub n plus 1 for all n. Kaya mono yung prefix dun sa term na monotonic. Kasi dapat isa lang yung behavior. Either it always increases or it always decreases. Okay, isa lang yung behavior ng sequence. Okay. And it turned out that monotonicity is a sufficient second condition to boundedness to guarantee convergence ng isang sequence. So siya yung tinatawag natin na Monotone Convergence Theorem o yung MCT. Okay. So let's try to prove it. Okay. Ang alam lang natin siya ay bounded, tapos siya ay kailangan nating mapakita siya ay convergent. Okay, hold on guys, sorry. Okay, I'm back. Sorry about that. Okay, so kung ang sequence ay monotonic at saka bounded, dapat siya ay magko-converge. So tingnan muna natin yung kung ano yung pwede nating masabi rito. Alright, meron kang sequence na monotonic at saka bounded. So kung siya ay bounded, ang ibig sabihin ng bounded, siya ay bounded above and bounded below. So what do we know about boundedness? Kung siya ay bounded, by the LUB property, magkakaroon siya ng supremum. Bakit naging clue sa akin na gumamit ng LUB property? Kasi ang monotone convergence theorem ay equivalent sa completeness axiom. So basically, yung equivalence na yon dapat dun sa proof ng monotone convergence theorem papasok yung completeness axiom, right? You can either do dedicants or sabi ko nga, operationally mas okay yung LUB property, mas madali siyang gamitin. So let's first try to see if that will bring us somewhere. It should, kasi equivalent niyang MCT sa LUB. So let's say, let's write it this way. So I'll have, oops. So I let AN be a bounded sequence. Dahil siya ay bounded, ibig sabihin siya ay parehas bounded below at bounded above. So meron siyang upper bound. So by the LUB property, okay, dahil meron siyang upper bound, meron siyang least upper bound. So we can say that the supremum of the ANs, okay, is equal to A for some real number R. Okay? So tapos, ang claim ko rito ay yung sequence AN ay magko-converge kay A. Kasi siya yung parang primal suspect. Siya yung posibleng maging limit ng sequence na AN. Alright? So let's try to see how we can show that indeed the limit is equal to the supremum. Okay? Alright, so basically yan yung makukuha ko sa pagiging bounded. And I think we're done with that. Gagamitin na lang natin yung monotonic. Okay? Now, what do we know about this? So we know that alam ko si A ay supremum. Okay? So therefore, okay. Ano nga ba yung alam nating properties ng supremum? Alright? So we go back to the different characterizations of the supremum. Ang ibig sabihin, ang alam natin before siya ay supremum kapag siya ay least upper bound, pero medyo hindi siya operationally easy. I mean, hindi siya madaling gamitin. So pupunta tayo dun sa characterization. Ano nga ba yung characterization natin ng supremum? Sabi natin siya ay supremum kasi pag binawasan mo siya ng konting-konti, by a little amount, say by an epsilon amount, hindi na siya magiging upper bound. So yun yung property ng pagiging supremum. So ibig sabihin, so for all epsilon greater than 0, there exists a, say, capital N. Capital N na ba gagamitin ko? Let's say. Sige, capital N na muna yung gamitin ko. Baguhin ko later kung hindi siya swak dun sa gusto kong mangyari, right? So for any epsilon greater than 0 that I can think of, there exists a capital N in N such that A sub capital N would be larger than A minus epsilon. Ito yung sinasabi natin kanina kasi ang idea rito ay kapag si A ang supremum, pag binawasan mo siya ng kahit gaano kaliit na positive real number, hindi na siya magiging upper bound kasi siya na nga yung pinaka maliit na upper bound. Pag binawasan mo pa siya ng konti, hindi na siya upper bound. So meron ng element yung sequence na mas malaki kaysa dun sa A minus epsilon. Okay? So, all right. So that's what we know there. Okay. One thing that we also know is that AN is increasing. Yun yung hindi ko pa nagagamit, yung pagiging monotonic, right? So now, without loss of generality, I will assume that AN is increasing. Pero parang dapat sa task ko pa to sinabi, right? Because kailan natin ginagamit yung W log o yung without loss of generality, we are assuming that this is true, all right? Etong assumption na to, without loss of generality, meaning kahit siya ay decreasing, all right, or monotonic decreasing, masusulat ko pa rin yung proof in an analogous way. Parang ito yung isang tanong dun sa problem set na nagpo-prove kayo na ang infimum ng A union B ay yung maximum between the infima of A and B. Tas ganun din sa supremum. Most of you just assume that infimum of A is less than or equal to infimum of B, which is fine. Pero it would have been better if you said without loss of generality kasi pwede mong pagpalitan yung roles ni A at saka ni B. Or kung hindi kayo sanay gumamit ng term na without loss of generality, dun sa ilalim ng proof nyo, pwede nyo sinabing analogous arguments can be made if yung reverse inequality naman yung totoo. Alright? Pero siguro this is not a nice place to put it. Lagay ko siya dapat pala dito sa taas. Be a monotonic increasing sequence. So dapat sa taas ko pa lang siya nilagay. So we let AN to be a monotonic increasing bounded sequence. Right? Tapos yung proof sa monotonic decreasing will be done analogously. Alright? So yun, pakidagdag siya sa itaas ng proof. From the beginning pala, dapat nilimit ko na to sa increasing. Kasi pumili na ako dito ng inequality. Alright? So makikita niyo kung bakit dapat sa taas pa lang sinabi ko na siya. Tinry ko siyang dayain at gawin siya dito yung pagiging increasing. Kaya lang hindi maganda yung kakalabasan nung narrative. So kailangan ko pala siyang ilagay sa taas. So nawalan ako ng palusot. Alright? Okay, so now we have the assumption that AN is increasing. So, okay, for all little n greater than or equal to capital N, we have, okay, we already know that A minus epsilon is smaller than A sub N. All right. Tapos alam ko nga monotonic increasing by assumption yung AN. So kapag ka yung little n ay mas malaki na kay capital N, yung A sub little n ay mas malaki din kaysa kay A sub capital N. All right. Pero ano pa yung alam natin about A sub little n? Si A sub little n ay term dun sa sequence, all right? Pero yung sequence meron siyang supremum. So this guy will be less than the supremum A. Right? Or meron pa yung equality, right? So least upper bound. Pero pwede ko itong dagdagan ng kahit anong epsilon greater than 0 and I'll get a larger number than A. And I want to do that because this long inequality here means that I have what? We have A minus epsilon is less than Nasa akin na lahat ng ingredients. Ang kulang na lang ay yeah. So this is A sub n less than A plus epsilon. All right? Tapos mag-add na lang ako ng magsusubtract ako ng A from all sides. I'm gonna have negative epsilon, A sub n minus A less than epsilon. Okay. And this continued inequality is the absolute value of AN minus A less than epsilon. And again, let's review what we have here. We have For any epsilon greater than 0, there exists a starting index capital N such that for all little n greater than or equal to capital N, yung a sub n minus a has magnitude less than epsilon. Okay? Which is basically the definition ng an converging to a. So napakita na natin na yung monotonic increasing bounded sequence an ay nagko-converge. And the proof did not just reveal the convergence of that sequence, pero sinabi niya sa atin kung kanino siya nagko-converge. Nagko-converge siya dun sa supremum noong sequence an, which we know to exist because we have a bounded sequence to begin with, tapos LUB property dictates meron siyang infimum. Meron siyang supremum. Okay? Now, this is the first case, and then you can just conclude yung proof niya by saying that an analogous proof can be written for a monotonically decreasing AM. Sorry, minamadali kong sulatin. Pero, yeah, kung ano yung kailangan yung baguhin para sa proof kung siya ay monotonic decreasing, dapat ang gagamitin nyo ay infimum. Alright? So, dahil siya ay infimum, so kailangan yung kumuha ng inequality, and then I think what you'll use here is characterization ng pagiging infimum. Kasi yung claim nyo, ganun pa rin. Magko-converge yung monotonically decreasing bounded sequence dun sa infimum. Tapos gagamitin nyo yung characterization ng infimum na pag dinagdagan mo siya ng maliit na epsilon, okay, hindi na siya magiging lower bound. So, baligtad tong inequality na to, magkakaroon ka ng a plus epsilon dahil decreasing siya, yung b little n ay mas maliit sa b capital M, and then you'll have similar inequality na kailangan yung i-manipulate. All right, but ultimately you will be able to show that that monotonically decreasing sequence Bn ay magkakaroon ng terms that in the long run will be within epsilon units away from the infimum. Okay. So a nice exercise is to try to write it down. Okay. Yung proof para sa pagiging infimum on your own. So try nyo siyang isulat. At least ngayon may idea na kayo kung paano pinuprove yung monotonic increasing. So to check if na-absorb nyo yung ginawa nating proof sa monotonic increasing, it would be a nice exercise if after an hour you'll try to write the proof for a monotonically decreasing sequence. All right? Okay. Then there is example 2.6 over here. I'll just put that as a reading assignment para makapunta tayo sa nested interval property. But let's do this after a 2-minute break. Okay? So pahinga muna tayo. And I need to take care of my runny nose again. Hold on, guys. So habang break tayo, chismisan muna. Parang umuunti na yung umattend ng klase 2, 4, 6, 7. So parang 7 na lang kayo ngayon. Pero actually, that's either still in the same level as other classes kasi ilan ba tayo? 25. 7 over 25, I think that's not too bad. Pero sa GC namin sa Math Division, parang concerned din yung mga teachers kasi paunti na ng paunti yung mga umattend ng classes nila. Is it because ang dami nyo na bang requirements ngayon? Ay, pero ito, here I am preaching about the survivorship bias, and yet I am committing it right now. I'm asking you guys kung ano yung dahilan ng hindi pagsipot. Pero kayo kasi nandito, so hindi kayo dapat yung tinatanong ko, ano. Pero anyway, yeah, marami na ba kayong requirements na kailangan ipasa? Yeah. Parang guilty ako dyan, Jericho, Last week, 155. This week naman, 175. So, kung tinitaking yung dalawang courses under me, yeah. And that's typical, right? Marami naghahabol ng requirements before the reading break. But I think that's a blessing in disguise kasi after that, medyo makaka-relax na talaga kayo during the reading break. So pagdadaanan nyo na lahat ng problema before you go to the break. Huwag kayong mag-alala, pare-parehas tayo may ganyang problema. Medyo hell week ko ngayon. I'm writing, actually kagabi I wrote a proposal. Binigyan kasi ako ng magandang problema. Kailangan ko raw sumulat ng proposal worth 200,000 para sa isang project for the IMSP. So, tinabaho ko yun kagabi. It's a nice problem, all right? So sana pag nag-face-to-face tayo, ma-implement na yung project na yun so you can benefit from it, right? Yeah, nasubmit ko naman siya kaninang umaga. Ang deadline ko pa naman ay sa 31. And then sa 31 naman, kailangan kong i-present yung proposal for a PhD in Data Analytics and Informatics. Hindi ko alam kung bakit ako yung nautusang sumulat ng proposal sa pagbuo ng PhD program na yon. Pero nirush ko rin siya, parang 2 or 3 weeks writing the proposal, and I need to present it to the graduate school or to one of the committees of the graduate school on Thursday. So medyo super hectic talaga. Pero looking forward to the reading break and the Holy Week para makapagpahinga ng konti. And pero gagawin ko naman pala nun yung yung modules ng 175. So, but anyway, at least paunti-unti, meron tayong natatapos. Okay, so let's go back. Now, another big name in analysis is the nested interval property. Hindi ko pa rin na-edit. Nested to dapat. Yan tuloy, nagduda ako. Hold on guys. Ano bang title nitong file na to? Yeah. Nakalimutan ko siyang i-edit last time, but it's the nested interval property. Now, what does the nested interval property tells us? So meron ka raw dalawang sequences. Mga AN at saka mga BN. Tapos ano yung condition sa dalawang sequences na yan? Dapat lahat ng AN ay mas maliit sa mga BN for all N. So yung corresponding terms kay BN ay mas malaki or equal sa corresponding terms kay AN. Sorry. Okay. Tapos ano yung second condition? Bubuo ka ngayon ng mga closed intervals. The left endpoint would be AN and the right endpoint will be BN. Now, the INs or this closed intervals are at least singletons. Kasi nga ang AN ay less than or equal kay BN, so well-defined yung bawat IN. Bawal kasi sa closed interval na mas malaking left kaysa dun sa right. It doesn't make sense to be a closed interval, right? Or an interval for that matter. So ang idea ngayon ay gusto natin na yung closed interval AN, BN ay superset ng interval A sub n plus 1, comma, B sub n plus 1. Kaya siya nested. Interval sa loob ng interval, sa loob ng interval, sa loob ng interval, and so on. Okay. So if these two assumptions hold, then we are sure that the intersection of all these nested intervals is non-empty. Okay? And moreover, if the length, right? Kasi yung BN minus AN, siya yung haba ng nth nested interval. Kung yung haba ng mga intervals ay nagko-converge sa 0, then singleton lamang yung laman ng intersection nila. And that intersection, that single element, kung saan nag-intersect yung mga nested intervals, siya yung limit ng AN at saka ni BN. Okay, pero nangyayari lang to kapag sure tayo na yung limit ng BN minus AN ay equal kay 0. Okay? Because otherwise, this intersection might contain more than one element. Okay? So mas madali itong mag-gets kapag may picture. Tingnan natin yung picture dito. Okay, so lahat ng mga unang condition, dapat ang AN ay less than or equal to kay BN. So si A1 definitely mas maliit kaysa kay B1, Si A2 mas maliit kay B2 and so on. The reason behind that is we want to have well-defined intervals. All right? So tingnan niyo yung first interval. Yung first interval ay A1, B1. Tapos gusto natin yung family of intervals natin ay maging nested. Kaya nested interval property yung tawag. In a sense that the second interval, A2, B2 must be a subset of A1, B1. Alright? So, ibig sabihin, tama itong picture. Kasi si I2, which is A2, B2, is a subset or it's properly contained in the first interval A1, B1. And that will be true for the rest of the nested intervals. So meron kang A3, B3, A4, B4, papunta kay A, B, papunta dun sa maliit na yon. Okay. Paliit yan ng paliit. Now, ano yung mga pwede nating ma-deduce dito? Okay. Now, first observation is that it seems that all of the ANs are smaller than the BNs. All right? Which is necessary, which is a consequence nung pagiging nested ng mga intervals. So, ibig sabihin, lahat ng AN ay mas maliit kay B1 for all N. Tama? Kasi nga, yung pagiging superset. Dahil superset ng lahat ng mga nested intervals si A1, B1, so yung left endpoints dapat hindi lalampas ng B1. Okay? So that means all of the ANs are bounded above by B1. So ibig sabihin, itong set ng mga ANs ay bounded above. E anong ibig sabihin kapag ka bounded above? Kapag ka bounded above siya by the LUB property, meron siyang supremum. So tawagin natin yung supremum ng mga AN to be equal to little a. All right? So LUB property in action na naman. That's why we can say after we envision the proof na ito talaga ay equivalent sa LUB property. All right? Now, we can also say na dahil yung mga BNs, silang lahat ay right endpoints ng mga nested intervals. So, dapat bawat isang BN ay mas malaki kaysa kay A1. Okay? Mas malaki siya dun sa pinakamaliit na left endpoint. So, hindi pwedeng magkaroon ng right endpoint na mas malaki, na mas maliit doon sa leftmost endpoint. So, ibig sabihin, the BNs, all of the BNs are greater than or equal to A1 for all N. Okay? So that means the sequence BN is bounded below. Merong lower bound yung sequence BN. And again, by the LUB property, kapag ka meron siyang lower bound, meron siyang infimum. Meron siyang greatest lower bound. Tawagin nating B yung infimum ng mga BNs. Alright? Tapos, makikita natin na, okay, kung ayan si A, so A could be somewhere here, and B could be somewhere here, alright? Kasi nga, yung mga BNs, ang infimum niya ay B, yung mga AIs, ang infimum niya ay, ang supremum niya ay A. Tapos ano pa ba mga natutunan natin about this, guys? So the A sub N's, necessarily, pwede mo siyang tingnan actually using the Monotone Convergence Theorem. Kasi yung mga AI ay yung mga ANs necessarily ay increasing. Alright? Kasi gawa ng pagiging superset ng mga nested intervals. So yung mga ANs ay increasing. So tapos bounded siya, bounded above by B1. So an alternative proof is to cite the Monotone Convergence Theorem. So magko-converge si A1 doon sa some number A. And the proof of the Monotone Convergence Theorem told us na, yeah, magko-converge siya, specifically magko-converge siya dun sa supremum. Okay? Now, meron tayong supremum A, meron tayong infimum B ng A at saka Bn respectively. Then the intersection, actually ay sure tayo magiging empty. Kasi ang laman ng intersection nila ay yung numbers na nasa pagitan ni A at saka ni B. Okay? So yun yung idea nung magiging proof dito. Na yung kasi gusto nating ipakita ng intersection nila ay non-empty. Alright? Kung meron kang isang x na nandito sa interval a comma b. So pag meron kang isang real number na nandun sa pagitan ng supremum ng mga an's at infimum ng mga bn's, ibig sabihin, okay, sila ay nasa lahat ng mga intervals. Kasi yung interval AB ay subset ng A4B4, subset siya ng A3B3, subset siya ng A2B2, and actually subset siya ng lahat ng mga INs. Alright? So yung interval AB, subset siya ng lahat ng mga INs for all n. Alright? Kasi si A, siya yung pinakamalaking left endpoint ng interval. Si B, siya yung posibleng pinakamaliit na right endpoint ng mga intervals. So, ibig sabihin yung closed interval AB ay properly contained dun sa mga INs. Dahil yung closed interval AB ay properly contained sa lahat ng mga INs, ibig sabihin yung intersection ng mga INs should contain the closed interval AB as well. That means the intersection of the INs would be non-empty. Kasi specifically, laman niya lahat ng laman ng closed interval AB. And that's apparent from the picture itself. Lahat ng nasa closed interval AB ay nandun sa lahat ng mga nested intervals. So, yun yung magiging proof na non-empty. Tapos pag sinama natin yung condition ng limit ng bn minus an, ito yung length ng nth subinterval, alright? Pag inassume natin na yung limit na yan ay mag-approach ng positive infinity, ang limit na yan habang si n nag-approach ng positive infinity ay equal kay 0, ibig sabihin paliit ng paliit yung interval AB which contains the elements of the intersection, alright? So ibig sabihin si A at saka si B ay palapit ng palapit sa isa't isa. Kasi by our order theorems, that means that si Bn at saka si An nagko-converge sa parehas na number. Tawagin natin yung parehas number na yun na si C. Okay. So, ibig sabihin nun, nagko-converge sila sa same number. So, ibig sabihin ito ay C, ito ay C. So, meron tayong closed interval C, C. Pero isa lang yung laman niya. Ang laman niya lang ay yung C. Yung closed interval C ay equal sa singleton containing C. So essentially, kapag yung limit na to pala ay naging equal kay 0, ibig sabihin parehas yung limit ni An at saka ni Bn, parehas yung supremum at infimum ni An at saka ni Bn respectively, then the intersection, okay, will just be a singleton consisting of the common limit. And basically, that's the claim ng nested interval property. Okay. Tapos hindi natin namamalayan, ito pala yan. Hindi natin namamalayan that is actually the proof. You see, a nice analysis of this picture here brought us to the idea for the proof. Okay. So dahil wala na akong oras, okay, so reveal ko na nga, yung proof ay nandito, tinakluban ko lang. So kindly read it, pero the idea behind it ay yun na yung kunento ko sa inyo kanina. Okay. Kaya lang dito pala, ang ginamit niya ay MCT. What I first suggested to use the LUB property. But it doesn't matter because LUB property is equivalent to MCT. Okay. Kaya nga meron na tayo ngayong medyo lumalaki na yung diagram natin. No? So meron tayong Dedekind's completeness. Alam natin equivalent yan via a remark sa LUB property. Tapos yung LUB property implies the Archimedean property. Okay. Ano pa ba? After ng Archimedean property, ano pang pinrove natin? I think yung squeeze theorem ay pwede rin idagdag dito, but we don't usually put the squeeze theorem. I need to check that. Kung pwede kong isama sa diagram yung squeeze theorem, but I think we can. But I just need to double check it. But at least after the Archimedean property, meron tayong monotone convergence theorem. Yun na nga ba kagad? Squeeze theorem, monotone convergence theorem. Tapos after monotone convergence theorem, kaya natin yung gamitin para ma-prove yung nested interval property. Alright? So, And then madadagdagan pa yan. On Thursday, we're gonna talk about ano pa nga ba after NIP? I think we have the Bolzano-Weierstrass theorem after NIP. So magkakaroon niya ng Bolzano-Weierstrass. After ng Bolzano-Weierstrass, magkakaroon tayo ng Bolzano-Weierstrass. Magkakaroon tayo ng Heine-Borel theorem. Okay? Tapos may mga dagdag pa yan. Alright? So lumalaki na yung multiverse natin ng completeness axiom, right? Density property, yeah, meron tayong density property, Michael, that's right. Though we don't usually put the density property as part of this diagram. Pero you're right. I think that's also a of course, it's a consequence ng completeness. Pero hindi ko alam kung hindi ko sure kung sufficient yung density property to prove yung completeness. Kasi di ba equivalence yung hanap natin. Kasi later, kahit one direction lang yung napapakita natin, halimbawa, yung MCT kaya nating gamitin para ma-prove yung NIP. Tapos next time makikita natin para ma-prove yung Bolzano-Weierstrass theorem, gagamitin ko yung nested interval property. Kailangan ko kasing i-close yung loop. So parang yung Heine-Borel, pwede ko mapakita na equivalent yan sa Dedekind completeness. Parang ganon. Alright? Pero hindi kasi ganun kasimple itong itong diagram na yan. May mga kakaibang routes na kailangan kong idugsong. Pero hindi naman para sa atin na i-prove silang lahat. Pang masters na yung diagram na yan. But just to illustrate to you the multiverse ng completeness axiom. Ano? But that would be for Thursday. So I think I'll stop here. 4 minutes overtime na pala ako. I think after the Bolzano-Weierstrass, may Cauchy convergence criterion pa pala. I forgot about that. Tapos susunod pa yung Heine-Borel. Okay. So yun pa, Cauchy convergence criterion. So we still have 3 big theorems to talk about. Hopefully we can finish it on Thursday para tapos tayo ng Unit 2 before the reading break. Okay. Babawasan ko na yung mga kwento next time para matapos ko siya. But do you guys have any other questions? All right. So if you don't have any more questions, then yeah, let's call it a day. Enjoy the rest of the day, guys. Tapos kita-kits ulit tayo on Thursday. Bye-bye.
Bye po, sir.
Thank you po, sir.